In C++, programmers like us have control over the memory and the life cycle of every single variable we create. By default, every variable we've created so far has been stored in something called stack memory. Let's explore what that means. Every variable in C++ always has 4 things. Every variable always has a name, a type, a value, and a location in memory, or what we might refer to as its memory address. Notice that in this example below, we have an integer with the name prime number and its value is 7. So here, the type is int, the name is prime number, and the value is 7. The memory address is not known, but we can explore where this is going to be stored based on how we created this variable. In C++, we can actually get at where the memory is stored by using the ampersand operator, and that's going to return the memory address of a variable. Let's see how this actually works. In this program, we see that we have our main function, and we know our main function is going to be the first thing that runs. Here we define a new variable, an integer, that has a type of int, a name of num, and a value of 7. So we know somewhere in memory, we have enough space to store an integer, and this memory is going to contain the value 7. The first thing we're going to print out to the console is the word value, and then print out the value of the number, and that's 7. The next thing we're going to print out is the address. And the address of the variable is going to be printed out by using ampersand numbers. So we're asking the C++ language to give us the address where that memory is being stored. Because we're going to learn that this is a stack memory address, we're going to expect this address to be a somewhat large number. So this number might be FFFF27242. Notice that this number has a whole bunch of digits to it. It's written in hexadecimal, and it's going to tell us exactly the address of the variable stored in memory. The address is going to differ depending on what system you're on. So when I run this program, I'm going to see a large number, but the exact large number is going to be different than the large number that you're going to see when you run this code. Let's go ahead and run this program and make sure that we see that this variable does have a value of 7 and see that the address that we find is indeed a large value. So let's head over to the console. Navigating into the CPP memory folder, I'm going to run make to go ahead and compile the code. And the program that we just looked at was the address of program. When we run the address of program, we see that the first thing we print out is value 7, exactly what we expect. And then the address is a very large number. Here on this system, it's 7FFFF-C59CA388. So given the length of this number, that's 12 or 13 hexadecimal digits long, we know that this is a very high memory address, which is exactly what we expect of stack memory. Let's look at why this is a high memory address and understand exactly how the memory works in our computer. As mentioned, stack memory is the default memory for all variables in C++ to be placed. So if we haven't done anything special, we know our variable is going to be in stack memory. Stack memory is specifically associated with the current function, and the life cycle of this memory is the life cycle of the function. So if you declare an integer inside of the function, that integer exists as long as that function is still running. When the function finally ends or the function finally returns, then the stack memory for that function is going to be released back to the system. So the life cycle of any variable created inside of a function is exactly as long as the function is being ran. One important property to remember about stack memory is that stack memory always starts from high addresses and then grows down towards the low addresses. So we're going to start at the highest spot in our computer's memory and start adding variables up at the high memory, growing down towards 0. So as we saw in the previous example, we start with a huge address, and we're going to keep moving down and down and down the memory addresses, which may seem a little bit backwards, but system designers chose to start stack memory at high addresses and grow down towards 0. Let's see this example happen when we have 2 different functions. So the very first function we have is the same main we had in our previous program. We declare an integer named num, and its value is 7. If we go ahead and draw the memory layout diagram, we know the first thing created in our memory is going to be the variable num that has the value of 7. And this is going to have a very, very high address because it's in stack memory. After we've added num to the stack, while main is still running, we're going to jump into the function foo. And the function foo is also going to live in stack memory. And here in this foo function, we're going to grow down towards 0. So the next address we see is going to be the address of x. So somewhere after the address of number is going to be the address of x, which has the value of 42. So what we expect from the console is we expect the first output to say that num is equal to 7. We expect the address of num to be a large value. The third thing we expect to see is that x is going to have the value of 42. And the last thing we expect to see is the address of x is going to be a large number, just like the memory address of num, except for it's going to be slightly smaller, slightly closer to 0, because we see that foo is below where main was running. So main is running, it allocates the memory for num. After num's been allocated, foo is called. So foo's allocation has to happen below the allocation for the main function. We'll notice that it's going to skip a little bit of memory, and that's just the overhead to call the foo function and some C++ internal maintenance. The big idea is we expect num to have a higher memory address because it was allocated first than the memory address of x. Let's go ahead and run this program and see if our understanding and our hypothesis actually check out. Here, looking at our console again, we've already compiled our code, and now I'm going to go ahead and run the program foo. In foo's output, we're going to analyze it and see that the first thing that happens is num's value is 7, and its address is a large number ending with 908. Then x's value is 42. The memory address of x is the same large number, but ending in 8BC. So 9 is a larger number than 8. So we see that the memory where num is stored is 908. The memory where foo is stored is 8BC. 908 is a larger number than 8BC. These numbers both in hexadecimal. So that means that everything about our understanding of how this works makes sense. And you see an example right here. The memory address of num is larger because it's been allocated first. X being allocated second has a slightly smaller value. So we saw this actually happen in real code, and I encourage you to run this program yourself and see how the memory addresses on your computer, they're going to be different because the layout of the memory is going to be slightly different and is randomized. But you're going to see that num will always have a memory address higher because num was allocated first in our program. Awesome. Let's go ahead and talk about how we can actually use these memory addresses inside C++ to help us keep track of all of this memory. One key idea in C++ that makes C++ so powerful is the idea of a pointer. All a pointer is it is a variable that stores the memory address of data. I like to think of pointers as simply an indirection away from our data. So if our data is here, 42, and maybe that's stored as an integer, a pointer is basically going to be a level of indirection away from data. We follow the pointer to where it's pointing to, and we notice that pointer is now pointing to the memory that's storing 42. Pointer itself does not store 42, but the pointer stores the memory address of 42. And if we follow the contents of the pointer, we get to our memory address. Pointers are so fundamental to C++ that the addition of a star to the type of the variable denotes that as a pointer type. Notice here we have an int star as the type. So the type of the variable is int star, the name is p, and the value of what's stored in the integer pointer is going to be the address of the variable number. So we know that there's a type, a name, and a value, and this integer pointer, because it's being declared normally, is going to be on our stack. So now we have an integer pointer that stores the value of where num is actually stored in memory. The very last thing we want to mention is often we're going to have these pointers and we don't actually want to know what the contents of the pointer is. We want to know what the contents of the thing it's pointing to is. And C++ provides us a dereference operator. So given a pointer, a level of indirection can be removed by preceding the variable with an asterisk. So notice this gets a little bit confusing because if you append the type of the variable with an asterisk, it becomes a pointer type. When you actually use the variable, if you prepend it with an asterisk, then that variable will remove the level of indirection. You'll dereference the memory address and get the actual value. So looking at a quick sample code before we look at a full program, here we have integer num7. So we have a piece of memory that's name is num. It has the value of 7. Then we have the variable p, which is a whole nother chunk of memory. It is a pointer, and it points to the address of num. The value in num is a third variable, and this value in num is going to take on the dereference value of p. So we're going to look at p, and once we see what p is pointing to, then we can go ahead and copy that value, 7, into value in num. Notice that the last line here, we do something different. So now that we've copied num into value in num, we say the dereference value of p should be made equal to 42. So we look at p, we follow that to where it's being dereferenced, and we change that value from 7 to 42. And the final state of this program, we have num that contains the value of 42, p that points to the memory address of num, and value in num is going to have the value of 7. One thing I think is really useful is to really look at how all of this actually works in memory and see if we can make sense of it. And as we do it, we're going to uncover a little secret in this puzzle that we see. So in this program, we've got our puzzle.cpp, which you also have in the code associated with this lecture. And we see that we include cube.h. We're using UIEC cube, the standard include file plus the using statement. And now we're going to go ahead and look at the main program and start running this program as though we're a computer. The first thing we do is we create a cube pointer C that we're going to put onto main stack. So the first thing that happens is we're going to allocate an area of this memory for main. So we'll call this main stack. Inside of main stack, we see the first thing we have is a cube pointer. So the type of this memory is going to be a cube star. The name of it is C. And it's going to take on the value of create unit cube. So create unit cube is a function. This function returns a cube star. So here we have a cube. So let's go ahead and create a create unit cube stack frame. This create unit cube stack frame, all of the memory associated with create unit cube is going to go down here, further down in memory. And we create a cube called cube. The type is cube. The variable name is cube. And this is a cube. We set its length to be 15. I'm going to just draw a 15 in the middle of the cube to note it's 15. And then we return a memory address to the cube. So that means create unit cubes, return value is cube. And that means that C points to this stack memory. So I'm going to redraw this to clean it up just slightly. And we're going to see exactly the same thing with a pointer from main's memory into cube's memory. At this point, we have the exact same drawing we drew earlier, and we have main stack frame, we have create units cube stack frame, and we see that the cube is here in create unit cube, and we have a pointer that points to that cube. One thing you'll remember is we said that the stack frame exists only so long as the function is running. So here on line 16, we return the memory address of cube. But because we've returned from that function, we see that this memory is no longer allocated to us. It's not our memory anymore. So I remove the orange box to say that memory has been deallocated by the system. It may not be reused yet. We don't know what's happening in that memory. It may still be our cube, it may not be our cube. But if we run some other function, the operating system almost certainly is going to use the memory that we were just using for create unit cube and that other function, overwriting that with some other data. So what we expect in this puzzle is that when we run some other function, that something crazy might happen to our memory, and our memory is not going to be exactly what we think it should be. If everything runs as defined, we expect that the surface area of this cube is going to be 6 times 15 squared, and the volume is going to be 15 cubed. So they're going to be nice whole numbers, don't have any decimal points, because all we're doing is squaring and cubing 15, and we expect those numbers to 15 cubed to be in the range of a couple thousand. 6 times 225 is going to be in the range of about 1,500. We expect when we print out data for the surface area to be 1,500, the volume to be a few thousand, and we can run this puzzle.cpp and see exactly what happens. We still have all of the old code we ran earlier, and we've already made it, so we can actually see that the compiler's already trying to warn us about something that's happening. So the compiler knows that in our puzzle.cpp, the address of our stack memory associated with local variables is being returned. That means we're already doing something we shouldn't do, and the compiler is helping us out by warning us this is almost certainly a mistake. When we run this code, /puzzle, we see that nothing prints out. And that's because we don't have a cout. So I can go ahead and open up the source code for this, and I'm going to add a little bit of cout to this code. So here on line 10, I'm going to include IOStream, and then I'm going to go ahead and cout the surface area, which is the value A. And I'm going to cout the volume, which is the variable V. So here in the source code, all I've added is 2 cout statements on line 24 and 26 in the provided code, which outputs the value of the surface area and outputs the value of the volume. I'm going to go ahead and save this and close the editor, remake it, and then run this code, /puzzle. Here we see the surface area and the volume are 0. That's absolutely not what we expected, but was a result of that memory being reused by the system for another purpose that just happened to fill up that memory with zeros. So even though the cube should have had a volume of several thousand, the cube actually has a volume of 0 because that memory was overwritten, because we returned a value from a function after the function runs. So the big takeaway from this puzzle is to understand how memory is actually allocated and how memory works, and to never return a reference to a local variable. So you'll rarely experience this, but once you start working with pointers, especially once we get into this week 5 and 6 of this course, you're going to see that this kind of stuff is going to come up, and you're going to always be mindful of exactly what you're doing with memory. Before we wrap this up, let's look at one final piece of code to kind of cement everything together. So here in our final program today, we have a program that sort of does a little bit of everything so that we have a complete understanding of how we expect the system to work. Going with our standard example before, we have a memory allocated called num, and it has the value of 7. And then we expect the first thing to get printed out is num has 7. The address is going to be a very, very large number. The number is going to be slightly different on each system it runs on, but it will always be large. The second variable we allocate is going to be p. P is a pointer that we set to be the address of num. So p, which has the address of num, the contents of p should be this exact number right here, because the value p contains is the memory address of num. So the contents of p will be the exact value of the memory address of num. The memory address of p is going to be right below the memory address of num. So remember, the values start high and grow down. So P's memory address should be slightly smaller than num's memory address. And finally, we want to dereference P. The dereference of P says we're going to follow P's pointer and see what it points to. P's pointer points to 7. So we expect 7 to be the output here. We expect this to be a large number, slightly smaller. So 2300 maybe. So we expect the output to be 7, large number, large number, large number, slightly smaller, then 7 again. The last thing we do is we change the dereference value of P to be equal to 42. So we change num to value to be 42. With num's value of 42, we go ahead and say P is changed to 42, and we print out what num is. So even though we never change num, we change the dereference value of P to be 42. So num's value here is going to be 42, because that's what's stored in memory. So the output we expect to see is we expect to see the number 7, which is the original value of num, a high memory address again, a high memory address that's slightly closer to 0, the dereference value of P, which is 7, the fact that the dereference value changed to 42, and then we expect to see 42 printed out. Let's run this program and see exactly what happens. So here in our final program, we run /main. And /main, we see that the output is 7. We see another very large number. And then we see this number ends in 148. We see this number 148 again, exactly what we expect. Then we said the fourth thing we're going to see is a memory address that is slightly smaller, which is exactly what we see. 148 is a larger value, 140 is a smaller value. The dereference value of P is 7, which we know that because it points to num itself. When we change the dereference value of P to 42, we see that num also changes to 42. So we have both seen in a program and understood exactly how this memory interacts with the system, and we have code that runs that shows this memory happen in practice. This is one of the hardest things to grasp your head around in C++, especially as it comes to pointers. We're going to follow up in the next lecture with heap memory, which includes a lot more pointers. And then after that, we're going to just do an entire video on just puzzles with pointers. So we're going to do a lot of this, and I encourage you to play around with this stuff to really get a grasp on exactly what pointers are, because they're a key idea in C++, and they're going to unlock the true power of all the things we're going to do in C++. I'll see you with heap memory in the next lecture.